Professor Joseph Wolf from the University of California at Berkeley. And the title of his talk is The Geometry of Complex Manifolds Related to Group Representation Theory.
It's a pleasure to be here, and I want to thank the organizers for the invitation and for doing such a wonderful job. And I want to thank Marcos for providing the occasion. Now, I'll repeat something I said to him privately. It's always a great pleasure when somebody who's so much younger than I am reaches his 60th birthday. So I'm going to talk about some geometry which has been at the basis of certain activity in algebraic geometry and in representations of semi-simple groups. First, let me remind you of a situation that everybody here has certainly seen many times, involving the Riemann sphere, stereographic projection, and the unit disk. So you can think of the lower hemisphere as corresponding to the unit disk. And then the Cayley transform consists of, you take the disk, you stereograph back to the lower hemisphere, you rotate 90 degrees, and you stereograph back to a half plane. So I want to use that idea, and this is the case P equal Q equal 1 of the following situation. You take, say, the Grassmannian, of, let me ask, is this visible in the back row? Of Q planes in complex P plus Q space. Only instead of P plus Q, I want to think of it as P comma Q, where the P are the pluses and the Q are the minuses. So now I look at the negative definite Q planes, and they form a homogeneous space under the special unitary group for the corresponding Hermitian form. Let's determine the stabilizer is part that preserves the P plane, or the complement of a fixed Q plane, and then determinant 1. This is the case P equal Q equal 1. Now notice something here. This is a complex symmetric space. You can think of it as the space of P by Q matrices that satisfy identity minus Z star positive definite. And this sits inside a complex Euclidean space, dimension P times Q. And there it sits inside a compact form of the same thing, the whole Grassmannian of Q planes, positive definite or not. Now the general pattern here is that you have a so-called Hermitian symmetric space that is a complex, a symmetric space with invariant, a Riemannian symmetric space with invariant complex structure. And you want to put it inside a complex vector space. There's a bounded domain. And the convenient complex vector space, of course, is its holomorphic tangent space. And that sits inside a compact form, which is going to look in the following way. So this is a compact, simply connected homogeneous Kähler manifold, if you prefer. So it's a particular case of, the compact one is a particular case of compact simply connected homogeneous scalar manifold. And this is the viewpoint from the compact group, the group of Riemannian isometries, or if you prefer, Kähler isometries. From the complex viewpoint, so this way you see the metric, and this way you see the complex structure, this so-called complex flag manifold. That's the same as a homogeneous projective variety. So from this viewpoint, you see the complex structure. And the way these things are used in representation theory depends on taking the group of automorphisms, taking the maximal compact subgroup. So this will be a complex connected, compact connected semi-simple group, and this is the centralizer of a torus. Now you look at its complexification. This B mod is so-called parabolic subgroup. What's a parabolic subgroup? This is the definition. The quotient is a homogeneous projective variety. Now the way these things are used in many situations, if you want to do anything analytic with the bounded, corresponding to a bounded domain, is you have another real group. These two have the same complexification. I'm using a certain grammatical approach here because sometimes there are several groups being used at the same time, and they're close relatives, cousins, parents, whatever. So this is the complex one, this is its compact real form, and this is just some other real form, probably non-compact. So now let's get back to the situation where G naught, of course, sits inside G and it acts here. So we have some G naught orbits. Let's give these things some name. I'll call this thing, say, Z. And the things that correspond to bounded symmetric domain would be the open orbits. Well, first, of course, you have to check that there are open orbits. But using a little bit of Lie group theory, you could, and structure of parabolic subgroups, you could check that there are only a finite number of orbits. So some of them must be open. Anyway, you look at open orbits, and if you want to do anything with them, you have to have something familiar so you can make estimates. And the most familiar thing is the one we started with, the unit disk. So now there's an important structure theory of Harishchandra. I'll describe the idea of the argument in a few minutes, but first let me describe the result. So here we have D. This, say, is let me go back to the bounded symmetric domain. And that's sitting inside some complex vector space, and that's sitting inside the compact Hermitian symmetric space. And of course, this is just an open G naught orbit. Stabilizer is a maximal compact subgroup, and this is homogeneous space for the complex group. And inside this bounded symmetric domain, you have some you have a product of unit disks. You have a product of unit disks. I'll give you an example in a moment with the Grassmanni and see where these come from. And these sit inside a product of Riemann spheres. So that's the situation we started with. Your unit disk inside a Riemann sphere is the lower hemisphere. Now, in general, for a bounded symmetric domain, you have a product of these things sitting inside a product. Let me give you an example with the Grassmannian. Let's see, I don't think I'm going to be the first person at this conference to write a matrix, but anyway. So the idea is this. I want to look at the unitary UP Q, unitary group, determinant 1, P pluses, Q minuses. And in there, I'll look at matrices. I'll divide them up P by P, Q by Q. And there, now I hope this is visible. First, I look at this U11, SU11, that's for a unit disk, involving the first and the P plus first variable. If I can think of this inside a projective space. And then I do, for the next, that'll involve the variables 2 and P plus 2. And I keep going until I bump into something. So I can do this the number of times equal to the minimum of P and Q. That's the so-called rank of the symmetric space. And what's going on here? In terms of the Lie structure theory, these correspond to some roots, non-compact roots, because this will be like a U11. This corresponds to some non-compact roots, which are, well, where the corresponding three-dimensional subalgebras don't interact. The sums and differences of those roots are not roots. The Lie product is 0. So these are so-called strongly orthogonal. There's a machine there that says it kills echoes, but I guess I managed to fool it. So-called strongly orthogonal roots. So the roots refer to Cartan subgroup consisting of the diagonal matrices. And so-called root spaces are the joint eigenspaces under the Lie algebra bracket onto itself of this Cartan. And then the joint eigenvalues are called the roots. And sometimes the sum of two roots will be another root, or the difference may be another root, or it may be that neither. This is the case of neither. There's a formula for how many times you can add or subtract two roots and get a root. And in particular, this implies orthogonal. So we'll write it this way. Okay, now let me say this in more Lie theoretic terms. So here's for SU8. Let's suppose now I'm looking at, this will be a special one because I'll be looking at, say, SU of 3 and 5. So this particular root corresponds, these are the, you put an ordering on the roots and you look at, and you have a system of positive roots. Then you look at the minimal positive roots, so-called simple roots. And this will be the non-compact simple root. And then now I want to find, well, so this will be rank 3, minimum of P and Q is 3. So I'll have this one, and then I'll have the sum of these 3, and then I'll have the sum of these 5. That'll give me a set of strongly orthogonal roots. So I'll have a 3 disk inside a 3 sphere. Well, one can write down many other examples. And the way this is used, incidentally, here K is the maximal compact subgroup. It has a circle center, and that gives the complex structure. And so now you can look at finite dimensional representations of this maximal compact subgroup. Holomorphic vector bundles. It's compact. They have a Hermitian metric. You can look at the space of L2 holomorphic sections. G0 acts on it because it preserves everything that goes into constructing it, and preserves the L2 product. Of course, there may not be any, but if there are some, then you get a unitary representation of the group G0 on space of L2 holomorphic sections. That's so-called holomorphic discrete series. Historically, that was the first one constructed in, well, there are several series of representations for semi-simple Lie groups, and this was the one that's in some sense the most geometric and the one that's in some sense the most accessible. And people often try to somehow use the ideas of the geometric construction involving something like holomorphic sections of bundles in order to find enough representations of G0 to do harmonic analysis. Now, one of the catches, if we go back to, if we don't look in this situation, well, let's first look in this situation. See, the maximal compact subvarieties here are the single points. I mean, this is contractible. In a more general setting, you have a so-called flag domain. You have a open orbit. On a flag manifold. So this is a complex, semi-simple, or say Lie group, parabolic subgroup, and this is open G0 orbit, say G0 of some point, Z0. And you want to do something like this. You want to look, say, understand the structure. This could be more complicated than a bounded domain. First, you look at the maximal compact subgroup, and yet, of course, it acts here. And the action has an interesting property. The property is that you look at the K0 orbits on D. So this is a complex manifold. It's open inside this homogeneous projective variety, or compact scalar manifold, however you want to say it. This is complex. That's a real group. So a real group, well, there's no guarantee that its orbits will be complex, with complex submanifolds. But the fact is that there exists exactly one K0 orbit on D, which is complex. Well, you just have to write down the condition for the holomorphic tangent space to equal to its image under the almost complex structure, and see that that pins things down in terms of the structure of the Lie algebra of G0, the Lie algebra of K0, and the Lie algebra of Q. And so this is in some old paper of mine from the 60s. Anyway, it's still true. And so now, in the bounded symmetric domain case, that's a single point. But here it could be something much more complicated. let's look at the Grassmannian situation again. The Grassmannian situation, we're looking at negative definite Q-planes in complex space with Hermitian form of signature P and Q. And now, and the group was well, as far as it's action on Q-planes, scalars don't do anything. So let's just pretend it's the whole unitary group instead of determinant 1 in there. Now you want to see which are the open orbits. Well, you take a Q-plane. If it's in an open orbit, what are the orbits are just given by the restriction of the Hermitian form to the Q-plane. See what the signature and nullity are. And of course, the open orbit we started with was negative definite. Now, if you take a Q-plane, and if it's in an open orbit, that means if you shake it a little bit, it's going to stay in the same open orbit. You just be careful not to shake it so much that you hit the boundary. Okay. So those are the ones where you don't have any nullity, because if you had some nullity, you could move it a little bit, and suddenly that part could become positive definite or negative definite. So the open orbits consist of the non-degenerate Q-planes of a given signature. So the signature could be 0Q, or it could be 1Q minus 1, and so on until until this hits 0. So, but of course, this also has to be bounded by P. Okay, so you see exactly what they are. Now, suppose I look at something of signature, say L and Q minus L. What's its stabilizer? Its stabilizer inside that unitary group would be, well, there would be a U of L and Q minus L, and then there'd be, for preserving the Q plane, and then there would be, well, while you're at it, you have to preserve the ortho complement. P minus L and I'm sorry, yeah, P minus L and L. This has to add up to Q, and this has to add up to P. Okay, so what is the maximal compact subgroup of this looks like? It looks like U of L and U of Q minus L and U of P minus L and U of L. And see what you're going to get out of this is a product of, what you can get out of this is going to be, I'm sorry, that's going to be the stabilizer, and this is going to be the stabilizer under UP, maximal compact subgroup of G naught, and UQ. So the compact group is going to have an orbit which is a product of two smaller Grassmann manifolds. And it's certainly not going to be reduced to a point. And now if you look at holomorphic functions, you see, of course, they have to be constant on these compact pieces. And if you mess around a little bit, you'll see that you've got so many group translates of that compact subvariety that you can get from any one point to any other point by traveling along subvarieties where the holomorphic function has to be constant. So you're not looking for holomorphic functions anymore. In fact, you can find, not quite in general, but certainly in this example, in fact, whenever there's a G0 invariant Hermitian metric on D, you can find a exhaustion function whose Levy form has the right signature so that you can't expect cohomology of any sort in dimensions bigger than the dimension here. And if the bundle is negative, then you're not going to get anything in dimensions less than the dimension here. So the dimension of these maximal compact subvarieties is the dimension where you look for something to substitute for sections of bundles. So analytically, that's how the dimension of the maximal compact subvariety comes up. But how about question? So you would know to look for cohomology or harmonic forms, whatever. But how about trying to see if something is going to be L2? Well, the way that works classically for the bounded domains is that if you want to show that for a bounded symmetric domain, if you want to show that some section of a bundle is square integrable, you first use some K invariance so that you only have to look at the inside the polydisk, the product of disks, and then you just compute. So what you want to do is somehow have some sort of polydisk here in order to compute. So that's sort of interesting. So in order to describe how that works, I'm going to have to be a little more specific about the polydisk in the classical case, the case of a bounded domain, bounded symmetric domain. So the way it works for a bounded symmetric domain is, let's see, I'm going to have to use a different kind of letter for the Lie algebras. So let me use this for the Lie algebra. Okay, not. This is my attempt to write lowercase Gothic k. There are people in the room who know how it should actually be done, but I don't think I'm one of them. Anyway, and G0 for the Lie algebra of G0. And I'll drop the knots if I want to take the complexification. And inside K0, I have the Lie algebra of a maximal torus, K0. That'll also be a maximal that'll also be a maximal torus of the compact group, compact real form of G. And this actually is a Cartan subalgebra of G0. So now I can look at the roots. Relative to that Cartan subalgebra. Well, let me complexify. So I have G equal to T plus some roots. And the corresponding one-dimensional root spaces. Now, since T not sits in here, T sits inside the complexification. And so if I look at the Cartan decomposition under the symmetry, I can write with the Lie algebra of K plus what in some cases might be the space of symmetric matrices, the space where the corresponding to the complexified tangent space. Now I can talk about positive roots, and I can talk about the positive roots in such a way that this looks like the sum for the positive roots in S and the sum for the negative roots in S. And actually, the hidden parabolic here is going to be K plus S minus. Now, I should explain something here. One of the ways to make mistakes in this area is to get into a situation where positive functionals correspond to negative bundles, and negative functionals correspond to positive functionals, and keep track and lose track of how many times you switched sign. So I don't want to do that. It's just too much trouble. So I'll have S plus correspond to the holomorphic tangent space, and S minus correspond to the anti-holomorphic tangent space. That's why I'm putting a minus here. Anybody who does mostly does algebra would do it the other way because he wouldn't worry about the signs of vector bundles. Okay? Now I could talk about, since T sits in here, and this is stable under the Lie algebra product, every root space either sits in K or sits in S plus or S minus. So I'll call these the non-compact roots, the ones that sits in S, non-compact positive, non-compact negative. So now, this theorem of Harishchandra, which says that there exist, I'll say what L is in a moment, strongly orthogonal, non-compact positive roots. Let me give them names, C1, C2, up to C sub L. That's, L is just so-called rank of the symmetric space. And so for each of these, you've got a three-dimensional simple complex algebra. Let's look at it on the group level. And if I take the product of the base point, product of the images of the base point, which I seem to have lost, point corresponding to the identity coset, or if you're looking from G0 viewpoint, or the point corresponding to this identity coset, if you're looking at from the parabolic viewpoint. Anyway, I take the orbit of the identity component, I get a product of Riemann spheres. And if I intersect with the real group G0, and take the orbit of that, I get a corresponding product of lower hemispheres, or unit disks if you prefer. And anything which is, and furthermore, G0 can be written, let me just write, this thing is capital Psi. And let me write this thing as G0 of capital Psi, G of capital Psi, and so on. Just means all the little psis. And a classic theorem of Cartan specializes to tell us that G0 can be written as K0, G0 psi, K0, and G can be written as the compact form written as K0, compact form of the complexification So in fact, if I take the image of the base point, which is fixed under K0, then it says that G0 is obtained by taking this poly disk and swinging it around with K0. And G sub U, the whole flag, is obtained by taking this polysphere and swinging it around with K0. So anything that's So once you know how K0 acts, I mean, it's just acting like finite dimensional representation, you can certainly make estimates on anything that transforms finitely under K0 by looking to see what happens on the polydisk or the polysphere. And this actually has an interesting consequence. You're looking now on Z. You look at all the G0 orbits. So what are all the G0 orbits here? The G0 orbits are obtained by looking in the polyspheres these are really the same point, because these are all the base point. I mean, I don't know how to really draw this otherwise. And so the bounded domain is the product of the lower hemispheres. And you just see by Cayley transforming, which is just rotating the spheres under an element of K0, you see how many times you go to the boundary from the South Pole, how many times you go to the equator, or how many times you go to the North Pole. And those two numbers specify the orbit, because an old theorem of Kelvin-Moore says that you can do any permutation of these psi's from an element of K0. So it doesn't matter what order you write them in. So what matters for the G0 orbit only is how many times you go to the equator and how many times you go to the North Pole. Stay put means, of course, there's zero. If you go to the equator in each factor, you're at this so-called Bergman-Cheloff boundary of the bounded domain, the most convex part of the boundary. Now, what happens more generally, there's no way this could work because you won't have a point here. You'll have that maximal compact subvariety. So things are going to get a little bit more complicated. So let's talk about the maximal compact subvariety. Okay, so far what I've been talking about is old stuff, and now I want to talk about something which isn't quite as old. Look at the maximal compact subvariety. Let's again stick in the situation where G has a compact Cartan subalgebra sitting inside K. Otherwise, things get a little bit more complicated, and the idea isn't quite as clear. Okay, so we have the maximal compact subvariety. Now it's going to look like that. Q won't contain K0, and we're still going to look for a situation where we're still going to be in a situation where G0 is equal to K0 G psi K0. That's just as long as K contains a Cartan subgroup of G0, you still have this. Well, that takes a little bit of a proof, but anyway, it may not be completely obvious, but it depends on some theorem of constant, which tells you how you construct all the real Cartan subalgebras of a real semi-simple group. You start with the one that's most compact, and you do something which is analogous to the Cayley transform successively on a set of strongly orthogonal roots. So now I'm assuming that you started with the one that's actually compact, and then you Cayley transform as much as you can. So now you want to look at this. So So let's look at an individual one. So this will look at its piece in K. And then its piece in S. So that's three-dimensional simple. This would correspond in the case of SU11. This would correspond to the matrices A00 minus A, where A is pure imaginary, and that is to the the skew Hermitian matrices, and this would correspond to the Hermitian matrices. Okay, so now I can start writing down all 2 by 2 Hermitian matrices. But anyway, now if I look at the appropriate factor, Riemann sphere, I see that I can write this lower hemisphere as exponential of, well, let me write it up here where it's more visible. I can write this lower hemisphere as exponential of S naught of psi I applied to the base point. I don't know what to call it, Z naught. I don't need the part that leaves Z naught fixed. Now, if I go to this more general situation, I can actually write, this is for any open orbit now. I can write this now as K naught exp of, well, it's going to be corresponding S naught of cap psi applied to Y. So what I get is, over the maximal compact subvariety Y, I get a unit disk at each point. And that's going to sit inside K naught. I mean, not a unit disk, a product of unit disks, polydisk. And that's going to sit inside K naught, applied to exp. And I'm using this grammatical construction I mentioned, where you use the same letter for the same thing, but just keep track of which real form. So now it's a compact real form. So along Y, I have a family of products of spheres, polysphere, and inside there, I have the product of their lower hemispheres, and I swing it around with K, and that exhausts the flag domain. So now what's happened is that I'm really, in some sense, using an Euler angle decomposition. Well, this is like an Euler angle decomposition. And so I have this product of unit disks sitting inside product of spheres. Now there are only two catches here. Well, 2 catches that I've run into so far. One is that I haven't yet been able to prove that these are if I apply this to an arbitrary point in Y, I get a complex submanifold. Certainly if I apply it to the base point, it's a genuine Riemann sphere containing a genuine unit disk, or product of unit disks. But if I apply it to some other point, I'm not so sure that it's compact, or that it's complex. And the other thing, which is so far not quite as good as in the Hermitian symmetric space, is that I don't really know which permutations of these I can affect from K. I've worked out in a lot of cases, but I haven't quite finished the job yet. But let me point out that you can't expect all permutations because when you go to roots, you can have two different lengths of roots. And anything you can do with a conjugation is going to preserve the length of the root. There are two cases. Well, in most cases, you can have psi consist of long roots, all long roots. I mean, if there's only one root length, there's no problem. But if there are two root lengths, you got short and long. You can usually get psi to consist of all long roots, in which case, well, you run case by case, but I don't know a general theorem which says that you get all the permutations. But there are two cases. There are two cases where you can't get psi to consist of all long roots. These are the cases where G0 is the group of type G2, which with maximal compact subgroup of type A1, the non-compact real form of G2. There you get one short root and one long root, and that's the best you can do. And the other case is where G0, let me get the indices right here. No? So I'm not finding it. Anyway, so it's where G0 is SO of 2L plus 1 and M, where M is even, and 0 less than L less than M. Or is it less than 2L? So in that case, in both of those cases, you have one short, the best you can do is one short root and the other is long, so you can't expect all permutations. So one of the spheres or one of the disks in this product is going to be distinguished in some sense because it will correspond to a short root. And the others, it seems they're indistinguishable. Now, part of the point was that you could go to the boundary or to the other orbits inside the polysphere. And it's a relatively easy topological argument, just looking inside this thing and using the fact this is compact, to see that you can get to any G0 orbit by going to, in this polysphere, going to on some factors going to the equator from the South Pole, and another factor is going to the North Pole from the South Pole. And the remaining factors staying where you are. So you can certainly catch all the G0 orbits and do analytic things with them in this rather pretty picture of the polydisk sitting inside the polysphere. But what you don't quite know yet is to what extent this only depends on how many factors. So let me describe another, let's see, I believe I have 10 minutes left, is that correct? Yeah. Let me describe another use of the maximal compact subvarieties. So let me write, so I've got D, which is an open G0 orbit in complex flag Z. And I've got the complex maximal compact subvariety inside D. The unique K0 orbit, which is a complex submanifold of D. So now I can look at, say, M sub D, which I'll define to be the set of all, I guess I didn't give a name. So it's the compact subvariety, which is the k-naught orbit. Set of all translates by elements of the complex group, not the real group, but the complex group, which keep it inside D. And now I'll explain the topology on this in a moment. But I want to take the component that contains Y. Sometimes it's not connected. So what's going on is this. I look at M sub Z, said, well, complex group translates of that compact subvariety. Now the stabilizer of Y inside the complex group is just going to be a complex subgroup. And it's going to be a closed subgroup because Y is compact. So this is going to look like G mod some closed complex subgroup. So it's naturally a complex homogeneous space. And this one is open in it because since Y is compact and D is open, if I perturb a translate GY a little bit, it stays inside. So this is open in this complex manifold. So this has a natural structure of complex manifold. In fact, assuming G is simple, this will either be an affine variety or a projective variety. Okay. So this is so-called cycle space. Now, actually, there are two cycle spaces. There's also a classical cycle space from complex analysis where you have you look at all formal integral linear combinations of subvarieties of an analytic space, and you take their various components and you look at the ones of proper dimension and so on. But I don't want to, and sometimes they coincide. I mean, with the dimension, with the piece of the same dimension. Sometimes they coincide with this Barlet cycle space, but not always. But I'm just going to talk about this one. So now I can look at the cycle space. And I can look at the domain. And I can look at the incidence space. And of course, the point projects here, and the cycle projects here. Now, the way this works in, my apologies for writing bundles upside, well, no, I guess I don't have to do it. I can look at a homogeneous holomorphic vector bundle over D. I can pull it back. I can push it down. Now, if I take a negative, well, from something I mentioned before, I only have to look at cohomology in degree S, the dimension of the cycles. So I look at cohomology in that degree. And look, of E, the G naught is acting on it. It's a nice Fréchet representation. And I want to see whether it has anything to do with the analytic structure, say the L2 structure of G, or see if it's a unitary representation. whatever. So I pull the bundle back and I push it down. Now that's a double vibration transform, if you will. And because the fibers here are just the cycles. So we know their dimension, and we know how to push things down using theory of Leray. And knowing what E is in terms of representation of the isotropy of G naught at a point, we know how to pull it back. And with some appropriate cohomology vanishing, which we could arrange, that's an injection on cohomology in degree S, provided E is negative, sufficiently negative. And then we push down, we have the Leray theory. We get zero cohomology of a fairly explicit bundle here. And but the point is that this turns out to be a contractible Stein manifold. So all holomorphic bundles are holomorphically trivializable. Now this picture collapses a bit in the case of the bounded symmetric domain, but in any case, so when you have a bundle here which is naturally gives you a unitary representation, you can see exactly what you get. But when you start continuing the parameters, you want to do something where you can compute. And so sometimes you can manage using the polydisk theorem, although the polydisk theorem is a lot newer than, a lot more recent than this construction. And on the other hand, you can see what the image of the cohomology is explicitly. Well, I should say that the fact this is a contractible Stein manifold is a result of mine with Alan Huckleberry. And to describe the image in terms of PDE is a result with Michael Eastwood. And that's essentially it's a generalization of the notion of Penrose transform. In any case, with Eastwood we have the PDE which describe the image, and then you want to do a holomorphic trivialization and use some PDE theory to get some information about the growth of cohomology classes and so on. Well, the obstacle there seems to be that there are too many holomorphic trivializations, and we haven't found the best one. Although in the Hermitian symmetric case situation, Harris-Chandra certainly found the best one. So let me just, in conclusion, say this is using the geometry of the maximal compact subvarieties inside these flag domains. The flag domains are very natural spaces. They're very often indefinite metric versions of bounded symmetric domains and things like that. Using the maximal compact subvarieties. So first of all, there's this work on trying to relate the geometry of the compact subvarieties to the harmonic analysis on G naught. And now there's this relatively new information with the polydisk theorem extended from Hermitian symmetric spaces. So well, the area is still pretty active. Let me just stop at this point.
Does anybody have a question for our speaker? Okay, if not, then let's thank the speaker again.